So our next speaker is Paul Emsley. So Paul started in structural biology in York, a campus full of wildfowl, it might be noted, working on hemoglobin. So for his postdoc, he moved to Glasgow to work on bacterial virulence proteins, but he was scooped twice. So he moved on to try and crystallize a membrane protein. And after several years, that produced no crystals. So Paul began to think that life in a lab wasn't for him. So in a hopeful move, he tried his hand at software for automated crystallographic solution. However, he came a bit sidetracked by trying to graphically view the results of phase improvement and model building. And this sidetrack developed into a main project, Coot. Paul then moved to LMB Oxford for a fellowship, and then his current position at LMB in Cambridge. And Coot is very, very popular. It's been cited, the paper's been cited somewhere between 70,000 and 100,000 times, so you're probably very familiar with it already. And I'll hand over to Paul.
Thank you. Start. Play. Okay. Thank you for the opportunity to speak to the organisers, Clemens as well, if you're listening. Right, but they did give me this title, Being Lazy in Coot, although it did get adjusted later, somewhat to my surprise. So I've taken that to mean, how can one improve one's productivity in Coot? And I'll be talking about the Real Space Refinement and the collateral damage, perhaps, the collateral changes in the graphics that came along with the improvement to the Real Space Refinement. So what am I going to do with this lazy thing? I took it to mean lazy in the way that it was used by Robert Heinlein in Time Enough for Love, the tale of the man who was too lazy to fail. The idea being that either he studied, or which was something he could do, or he had to be a ploughman, and he was too lazy to be a ploughman, so he did some studying. What that means in Coot terms, for you ladies and gentlemen, if you're going to be using Coot for model building, manipulating models and maps and things, then I encourage you to learn these shortcuts. It will improve your productivity. I believe that to be the case anyway. If you're not using Coot for such a thing, if you're merely looking at the improvements of maps because you're interested in a map generation program or a structure factor generation program, then really this set of shortcuts is not for you. Not really, because it doesn't apply to your usage of Coot. I shall try to point this thing at my face a bit more. Okay. Right. How do we find where these shortcuts are? Well, the whole of the GUI has been rewritten practically from scratch, and now it's more canonical and behaves more like a standard desktop application. I hope that was a design anyway. So if one is going to find these shortcuts, then you'd go to About or Help, and then look around there. And indeed, in that menu item, that's where one would find the shortcuts. And this is using standard representation of shortcuts as one would find in GNOME-based desktop applications. So about this talk, to address the question set by the people who invited me to talk, I'm going to be mostly talking about, well, to answer the question is going to be Real Space Refinement. And as a consequence of the changes that were necessary to improve the Real Space Refinement, I'm going to be talking about the graphics and using graphics in Blender, and just a slide or two at the end about Moorhen if you were not here this morning. So the second part of this, when you see part 2A, there's going to be nothing but pictures, hopefully attractive looking pictures, but you can be the judge of that. So Coot 1, over the years, we've had various versions of Coot in the 0.7, 8, 9, well, they started at 1, of course, many years ago. But now we have version Coot 1 and Coot 1.1. Why? Okay, so well, eventually I had to release some Coot 1, but why now? So 2016, I think, or maybe 2017, I forget, it was such a long time ago. CSP4 in the developers meeting, the core team, Charles, told us that CSP4 core team will be dropping support for Python 2. And if Coot were still to be part of the CSP4 suite, we, along with everybody else, that is to say, we needed to move to Python 3, just like everybody else. And because of the way the infrastructure for Python and the widgets that I was using to use Python in Coot, that meant that we had to upgrade the graphics to OpenGL 3 or 3.3 and GTK3. And what that meant is throw away a lot of the GUI and throw away all of the graphics and start again. So all of the Coot graphics have been rewritten from scratch. That's why we have the opportunity to re-represent, have another think about the ways in which we can represent models and maps in Coot now. I listened to Charles and I thought to myself, well, if I'm lucky, I can get that done in 6 months. 7 years later, here we are. October 2022, Jakob joined the team thanks to funding from Global Phasing. And just a couple of months ago, Coot 1.1 was released, and that is the version that works on Macintosh. That is the version that hopefully CSP4 will be distributing in a forthcoming version of the CSP4 suite. While we're talking about improvement to the graphics, one of the parts of the infrastructure that disappeared as we upgraded from version 3 to version 4 was so-called Canvas. So the whole of the infrastructure of drawing ligands in Coot disappeared. And so that needed to be rewritten from scratch. And that is where Global Phasing and Jakob Smolsky came in clutch, as it were. And so now there is this ligand building tool that is now part of Coot, and it also has an existence in, at least at the moment, a nascent form where it will be able to be represented as a web tool as well. Lahasa it's called at the moment. So you can sketch your ligand here or import something from the web. You can type in aspirin or something. It uses Wikipedia to convert names into INNs and from INNs into smile string via PubChem and things like that. So you can import molecules and then you press the apply button down the bottom right-hand side. And then you have access to, at least today, 2 model building tools that convert your 2D sketch or smile string, you can choose, into a 3D representation, which is the dictionary that is used by refinement programs. So those 2 options are ACE-Drug and Grade 2. Today, there's little effort to include Phoenix tools as well, if they'd like. So this talk is encapsulated in this figure in cartoon form. Coot has been designed from the beginning, really, to be an environment for model building, refinement, and validation. Over the years, the ways in which you can introduce validation and model building and refinement have changed, have been improved and extended, and the internal tools for model building, refinement, and validation also have improved. So it's partly my ability to program, partly my exposure, and eventually I was able to use multiple threads, so the refinement and multiple parts of the validation, rotamers, Ramachandrans, and body contacts, these are all multi-threaded now. And if you have 16 cores, then it will use 16 cores to calculate your non-bonded contacts. So this means that you get more frames per second and a more attractive look and feel when you're running the application. So the idea is that the Coot environment is one in which it's convenient, expeditious to do the model building, refinement, and validation together. In the early days of Coot, there was no Ramachandran plot, so we seriously thought that the right thing to do was press a button in the Coot. It writes a file to the file system, a PDB file, of course, and then runs ProCheck for you, and then displays a PDF. Obviously, we rejected that idea and built in a Ramachandran plot into Coot, and indeed many other validation tools along the way. So modern computers have multiple threads and discrete graphics cards. So multiple threading has allowed, as I said, dynamic validation, improved number of cores, improved architecture in megahertz and gigahertz, allows you to improve your frame rate. So the bigger and better computer you've got, the more easy and comfortable it is to use Coot. So as well as multi-threading the validation, the refinement is multi-threaded as well. And as part of the feedback from the refinement to the graphics, we can inspect the refinement, the particular parts of the geometry, so bonds and angles and chirals and non-body contacts, ramachandrans and rotamers. We can inspect those as they move between the refinement and representation in the graphics, and display them as health bars, interactive, multi times per second, updating validation. I've got a video in a moment and you can see that. It looks something like this. I won't dwell on that. So what's different these days? If we look at the top, is this a pointer? It's dangerous. That one? Apparently not. Ooh, buzz, it says. That didn't work. Right, top left-hand side, dynamic interactive restraint analysis. So that's what I mean by health bars. They're really damage bars. They are representing the ways in which your model is providing high energy components into the refinement. For an example, a distorted chiral center and a non-body contact that is too close to each other, a improbable rotamer or ramachandran set of torsion angles. It's interactive, which means that you can click on those parts of the health bar and you can be directed to that part of the structure as the refinement is ongoing. We get interactive dynamic assessment of the rotamer probability and ramachandran probability there. These days, it's represented as dodecahedron and spheres. What else did I want to say? Oh, yes. Previous versions of Coot had lots of dialogues where the idea is to do as Chimera X has done, and it's redesigned from Chimera. Reduce the number of dialogues, and it is considerably reduced, but they're not all gone. And part of that change is to have the dialogue that had accept, reject, the refinement has now disappeared, and the buttons are now built into OpenGL and displayed on the bottom right-hand side, so they no longer, and they're transparent, and they no longer cover the thing that you want to look at. And the Ramachandran part on the bottom left-hand side is interactive and dynamic. Well, I say interactive. Not today, next week it will be. You can click on the red spots, and as you move around the structure in 3D, the Ramachandran plot is updated to reflect the phi psi angles that the model currently has. Right. What you'll notice about the new version of Coot is that it is center first. So you no longer click on a residue to activate a function. Coot knows which residue you want because it's the residue at the center of the screen. And there's a tilde key which tells you which residue it is if it's not immediately apparent. And then you can select whichever operation that you want. You might want to work on a zone or a chain, and you press the tilde key and it tells you which atoms are moving in that atom selection. So you may be familiar with Chimera X and Isolde and Tristan Kroll's work, and I had the opportunity to watch a presentation from Tristan some years ago now, and he had this thing that in Coot is called updating maps. The idea being is that as you modify the model, you regenerate a map that is consistent with that model rather than a map that you get from the model that went into the refinement program. So if you flip a peptide, as if you were here this morning, if you flip a peptide, then the map will update to reflect the new atom positions. When I say flip a peptide, that's just one of the many operations you can do to manipulate the model. This was an idea I got from Tristan, and it was such a surprise that we have now access to hardware where that kind of update is available to us. Okay, so thank you, Tristan. Yeah, okay, I won't dwell on that technicality there. The idea being is that the modern interface is interactive and dynamic, and one can improve one's productivity with it if you get used to right mouse for rotate. Just like the Chimera, just like the Quanta days, if you remember those. So Quanta was right after all. If you can use that, then hopefully your productivity will be improved. Now I have a video here. Fingers crossed. Can you see that? Can you see it? Open. I click down here. No, you still can't see it. Okay. Okay. Right, can I flip it over here? Can you see that? If I do full screen now. Okay. Okay, I can't see what you're looking at. Right, so oh dear, this is going to be complicated, isn't it? Right, okay. So this new version of Coot, we have better rendering of models and maps. It's done with the thing called instancing, so that helps the frame rate. The interactive tool here is now the Ramachandran's, Rotamer's, C beta deviations, and a thing called atom overlap is what we're using. We don't use clashes in Coot. So here is a problematic non-body contact. You can also see that it is created can I keep up? It's too fast. Okay, so I turned on updating maps, and you saw that the map changed a little there. That means that Clipper is now in control of the map calculation, the structure factor calculation. So we're doing a recalculation from map to model. I changed the Rotamer. You can see the particle effects there. We're letting you know that the map has been flattened in that region. When you're doing model building, right, one of the things that you want to do is to improve the fit of the map to model, and that is apparent from the difference map. Okay, so I'm just going to tidy up the side chain here. The balls are green and the dodecahedron are green, so green is good, red is bad. We're going to change that at some stage this year, so it's better for colorblind people, because at the moment they just see everything orange. That's no help at all. Okay. Right, so as you can see, the left-hand side is now dynamic. So every time I'm updating the model, the number of problems of that structure are changing. It's reassessing it every time I change the model, because if I change a Rotamer, I may also be changing the non-body context, so that it all gets reassessed at the same time. So we got into something different here. I wonder what I'm saying. Right. Oh, yes. So this is the health bar, right? So I've turned it into the whole of the chain is a molten globule now, and it's dynamic and interactive. We have these dodecahedra that are red. And I flip or change a Rotamer. Does auto fit Rotamer? There's another one that's round the wrong way. Well, possibly round the wrong way. It's not very good fit to density. I do auto fit Rotamer and it fits. And am I going to do something else? Right, so those are the Rotamers. If I click on the right-hand side, the least probable is on the most right-hand side. Here's another one. Not only do we have a problem in the side chain, but we also have a problem in the main chain. I flip the peptide to give it some energy, and then it does an energy minimization from there. The main chain now fits the density, and which is, you can see from the green balls, but the dodecahedra are wrong. And hopefully you can see that if I do an auto fit Rotamer, it fits to the density, and we have a high probability chi angle set. What have we got here? Oh, so something that's orange here, this arginine. To my eye, that didn't really need changing very much, but maybe the guanidinium group at the end could have done with a tweak, which I didn't do. So we got something else here. This is a glutamine. And as you may know, there are hydrogens attached to the nitrogen atom here, and there are hydrogens attached to the side chain carbons as well. And in this conformation, it's improbable, low probability, because those hydrogens are bashing into each other. Let's twist it round so the oxygen's on that side. That interaction is removed, and we get a high probability rotum. Okay, so having done that, you can see that's cleaned up lots of problems on the left-hand side. So all of the model building problems, so rotamers, Ramachandrans, non-body contacts, they have been cleaned up. Now the only parts of them we want to look at is parts of the map that are not yet accounted for by a model. We can do that with difference maps or blobs. Let's look at the blobs. I'm just going to do a couple of blobs here. It's crystallized from ammonium sulfate. No surprise, this thing is, I teach in my tutorial, say, ammonium. Ha 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 ha. But of course it isn't, it's a sulfate. So let's stick a sulfate in, and the particle effects tell us we've flattened the difference map. And there's a little bit of density there. We could do a bit of B factor refinement if we wanted to. I say refinement, but what we do is change the B factor and then watch the Coot points accumulate. The Coot points are letting you know you improve the, oh dear, he's too quick. Why don't I press the stop button? Oh, because I can't find it. Stop. Okay. Moving on to the ligand binding site. It's done a text search. So monophosphate and guano. Which ligands in the PDB are guano? It reeled it in, the particle effects telling you that there was a non-body contact problem here. Now that's been resolved by the refinement. It's a green ligand, so it's not yet part of our model. So what I need to do is merge the ligand into the main molecule. And as I do so, it'll become part of the atom selection, the particle effects, again, letting you know that you've flattened the difference map, and you're moving on with accumulating in Coot points and reducing the RMSD of the difference map. And that's, I should finish. If I can only had a brain. Where's my pointer? Now, if I do this, will it take control? No, it won't. Okay. Go to here. Where's my pointer? Oh, there it is. There it is. There it is. There it is. Stop. Now, if I go back to my presentation, where's my pointer again? It must be down here somewhere. Come on, presentation. And if I full screen, oh, no, that's not full screen. Play slideshow. Improve productivity. Right, so that's where we were. So this is just a set of slides that, in case that video didn't work, which it almost didn't. I flip the side chain, the map improves. In this case, fit a main chain, which was missing before, and the map improves. I fit the phosphate, or sulfate in this case, map improves. I fit the waters, the map improves. You can see things getting flattened. Okay. With the improvement of the refinement, we can include large atom selections. So my colleagues have told me about a way in which we can change the target function for geometry. Instead of using Hooke's law, which is a harmonic restraint, there's a thing called a Gemin-McClure M estimator, so that when we have large deviations, the effect in the target function is reduced. So that's what is used in the domain refinement. So if you're moving around molecules for cryo-M, for example, then you can yank on an atom and the whole molecule changes. And the red and, sorry, that's not red, is it? The purple and the greenness show you the degree to which the restraints are unsatisfied as a result of your manipulation and refinement. I have 5 minutes left. So quickly whizzing through some graphics. Now that we have access to graphics cards, I can introduce frame buffer effects. So we generate the image and then use the depth buffer to add hopefully useful and attractive manipulations of the image. One of those things being screen space ambient occlusion. implicit shadows, and then explicit shadows because we know where the light is and where we know I is, and we can work out whether molecule is projecting onto itself, outlines and blurs. You may have been in the tutorial, the lunchtime bites. So here's an example of where I've done some atom selection. Said hydrogen's blue, ligand's purple, everything else kind of creamy colored. And I've turned on the ambient occlusion as well. So user-defined atom colors and ambient occlusion. Here we can use the B factors to represent the alpha fold 2 PLDDT. Here's the so-called Goodsell color scheme, where we do color by chain, but also there's a variation in the subtle change in the atom colors depending on the atom type. This is something from Lucrezia Catapano. Color by B factor with screen space ambient occlusion. This is the structure from the tutorial, and this is another one for bacteriophage base plate, color by chain, again with SSAO on. This is a neutron data set, and hopefully you can see in the back, the idea here is to look at the pretty density and the partially deuterated hydrogen. And the idea is that the structure in the background is not so important to the scene, and therefore it's darkened down and blurred out. So it's supposed to be artistic. Again, we can use additional lighting effects to do blurring, and here I've colored the map black, in fact, and using a shader that allows us to include what's called Fresnel lighting, or model thereof. We can easily see where the density is, even though the density is black on black. You can see where the density is because of the rim lighting, and it's rather useful and attractive. Well, you choose. To my eye, it is. libcoot API. So if you were here this morning, you may have heard Philo talk, but if not, libcoot API is what it does is splits Coot down practically down the middle and says there are parts of Coot which are library functions that operate on maps and molecules and return vectors and residues and things. And there are parts of the program that is for the representation. So let's throw away all the representation part of Coot and use the library. And on top of that, instead of having the GTK OpenGL interface, let's change the interface. Let's use a different one. And what we're going to do in the case of Moorhen is provide an interface to the web browser. But there's another way, which is you can see here Python or Blender. And so the third one down is what WebCoot Moorhen is, WebAssembly and JavaScript. And there may be even interfaces for Godot or Unity, where that molecular information can be plugged into a 3D world, maybe even a virtual reality 3D world. I haven't done anything work on that. I'll do it in one weekend in my spare time. So if you want to use Coot or libcoot API from Python, you're now able to do so. So hopefully you can read this. It's not too tricky. So this version of Coot is headless, the headless API of Coot. So that's why it's called Chappy. And you can ask Chappy to read a PDB file and then query, given that index, which is IMOL. So molecule number 0 is the thing that you got from reading the PDB file. And then you can ask of that anything. You can do atom selections, molecule minimization, or in this case, what are the residues next to residue 20 in the A chain? So extending the Python interface, this is something that Lucrezia Catapano has been doing. So there's a GUI now in Blender that looks something like this at the moment. And I'm no great artist, but I can use this to do things like inverted hulls, so that gives us an outline. I just follow the tutorials. Well, the tutorials are written for artists. They're just applied to molecular entities. So this is the ribbons representation of molecules to triangles written by Martin Noble. And that, again, has been exported into Blender for this kind of knitted crochet effect. We've got seafood, somehow Halloween seafood representation of cryo-EM reconstructions, peptides, materials. We can manipulate this kind of thing in Blender. You may be familiar with this image. Here I've done an atom selection and used that to select a map and then surface the map. And these are the tools now available in Blender for artistic representation and rendering of molecules. Again, we're using the Coot tools here to calculate masked maps and then Fourier transforms, or in fact, what I've done here is blurred the map. So it's smoother. You get this kind of smooth, glassy effect with a blurred, applying a blur to cryo-EM reconstructions. Okay, I'm going to run out of time. So as well as Blender and Python, Moorhen is Coot in the graphics browser. Although now, or that's what we did in the first year, it will increasingly become more than just Coot. It is now. There are tutorials now online that you can do publication quality images, and you can do modeling operations. Thank you to my colleagues who have been helpful with their discussions. So that's top left-hand side. Global Phasing has provided the funding for Jakub Smolski, who helped with the GUI, and the Moorhen team, as you may have heard this morning, is a great team to be working with, very productive, and it seems to me that Moorhen will be playing an increasingly large role in the future of, well, CSP4. All right, thank you.
So, I mean, I think we've reached time, so it's time for a break, unless people are willing to forego part of their break.
Someone got a very good question.
There was one in the chat, which was, what's the maximum number of Coot points you can get, which is...
Good, thank you. The Coot points are, well, if you completely flatten your difference map, then you'll get around, it depends on how bad your map was to begin with. I don't know the answer to that question, but 1,000 Coot points is a pretty good session. It's designed so, yeah, so that 1 or 2% is 1,000 points. R factor change, I mean.
What is the keyboard shortcut for turning on molten maps?
Model to map?
Molten maps.
Oh, Shift R. Oh, molten maps. Let's see what you mean. Update. Oh, calculate updating maps. That turns it on. Yeah. So I misunderstood your question.
All right. Can we thank Paul and all speakers again?